Hi everyone, this is Dr. Saida Falafini from Cal Poly Pomona. In this video, we are going to learn about open queuing systems. Open queuing systems, they are a generalization of queuing systems in series. So we still have J stations or J stages. We still have J stages of operations. The number of servers at each stage is Sj. At each stage J is Sj. Okay, so the number of servers at stage 1, we call it by S1. Is at stage 2 is 2. So this is just notation. There's nothing tricky about it. And the servers at each stage J provide service with the rate of mu J. And one other important characteristic of these systems is that customers can arrive from outside to any one of the stages. Okay, and that let's assume that happens with the rate lambda. This is something we didn't have in previous system. Okay, so that's one important difference. So the customers, so in previous system, when customers come to the system, they all go to the first operation, and then from there, all of them go to the second operation, third operation, fourth operation, kth operation, and then finally leave the system. However, here, we may have some entities that are coming to the first operation, but we also have some entities that are coming from outside, and they may go directly to the third operation, to the fifth operation, to the kth operation. Okay, so that's why basically we call it open queuing system, because apparently this queuing system is open to the outside, and the entities from outside can come and they can go to any one of these operations. So we have that. And then after completing service at each one of these stages, let's say stage I, then there is a probability Pij that these entities go to stage J to get the next operation, or they just leave the system. So again, the difference of this one and the previous system is that in previous system, we had a queuing system in series. When the entities came to the system, they went through all the stages. They had to go through all the stages, one after another. But here, that's not the case. An entity that comes to the system may get the operations in the first machine, and all of them may go to the second machine. And then from the second machine, some of them, let's say, may go to the fifth stage to get the operation. Some of them may go to the third stage to get the operation. It's not that all of the entities have to go through these queuing systems one after another in the order. So in that scenario, we can write it as once completing the service at stage I, a customer or an entity can join the queue in stage J with probability of Pij. Okay, so once the entity is done processing at the stage I, the entity can go to any one of the stages, let's say stage J, with probability of Pij. Okay, and keep that. Or the entity can leave the system completely. So the entity is done and it can leave the system. Okay, so again here, in previous system, we assume that the entity goes through all the operations one after another, and then the entity is done with the last operation, the entity is done. But here, depending on the type of entity and the process it has to go through, an entity that, for example, has is right now at the stage, let's assume there are 10 stages, and the entity may be at the stage 5 right now. And there is, based on the operations that should be performed on the entity can leave the system at that stage. The entity doesn't need to go through all the stages of the operation. The entity can leave the system right there, and the probability of leaving the system at any one of these stages is going to be 1 minus sigma Pij, j from 1 to k. So you guys get a better sense of what it means. So let's assume this is stage 1, stage 2, stage 3, all the way to stage k. Okay, stage 1, 2, stage I, all the way to stage k. And let's assume an entity is done at the stage I. Okay, we said that when the entity is done at the stage I, it can go to any one of these stages potentially with probability of Pij I1. So P-I1 would be the probability that the entity needs to go back and get an operation done in stage 1. Pi2 is the probability that the entity is done at the stage I, now it has to go back to stage 2 to get some operation at the stage 2, or any other of the stage. Pik will be the probability that the entity is done at the stage I, now is going to stage K to get some operation done. So in that scenario, if the entity is done at the stage 1 and wants to leave the system, what would be the probability that that scenario happens? The entity is done at the stage I, and the entity wants to leave the system.
That's the 1 minus sigma.
Exactly. Because when an entity is done at the stage I, something has to happen to the entity, right? Either the entity has to go to one of the other stages or has to leave the system. So one of these have to happen to the entity. And the sum of these is 1. So the scenarios I put here are everything that can happen to the entity except the leaving system options. So then the probability of leaving the system is 1 minus everything else. And everything else is just the sum of these probabilities, which I put as Pij, and J goes from 1 to K. So that's basically where I got this number here, that when an entity is done at any stage I, then the entity can go to any of the other stages in the system, or the entity can leave the system with this probability. And these are the probability of going to other stages in the system. Obviously, if you look at the problem and Pi1 is 0, what does that mean?
Then there's no possibility of it going back.
Yeah, exactly. That means for in that system, when an entity is done in a stage I, it never goes back to stage 1. That's fine, but maybe there's some other probabilities are positive. But so basically what I mean is that you don't have to have positive values for all these probabilities. So in the formula, I consider all of them as Pi1, Pi2, but in your specific case, if some of these transitions are not possible, just put the probability as 0 and that would take care of it. So then this is what we call as an open queuing system. And as you can see, now we basically are looking at systems with a lot more complexity, so which are closer to the real world situations. So then in this system, we can say that lambda j, which is the rate of arrival to any state j. Okay, let me go up. Remember here we said at this part that customers arrive from outside to any one of the stages in the system. And we said that rate is Rj. Okay, so we assume that the entities that come to the system, the rate of arrival is modeled like that. So the entities arrive from the outside. The ones that get to stage 1, they arrive with the rate of R1. The ones that get to stage 2, they arrive with the rate of R2. The ones that get to stage K with the rate of RK, with the rate of Ri, and so forth. So that's basically how the arrivals are modeled in this system. If, for example, in a system that you are looking at, let's say Rk is 0, what does that mean? R is just the rate of arrival of entities to your system, but they are the ones that are coming from outside, not the ones that are going from stage K minus 1 to K, or from stage 2 to K. They are the ones that are coming from outside.
Oh, then only people in your queue would arrive? No one outside the queue would arrive?
Yeah, so that basically means that if Rk, for example, is 0, that means in your system, no entity from outside comes and goes directly to state J. So the only entities that get to state J, they get to state K, are the ones that are processed somewhere in the system and then end up at the state K. But no entity directly from outside goes to state K. Okay, so again, these are general scenarios, general notations. I assume an Rj for each state J, representing the entities that are coming from outside and go to state J. However, if Rj for any state J is 0, that means no entity from outside comes and directly gets to that stage, and that's perfectly fine. Then the only entities that get to that state are the ones that are coming from some other stages in the system, and that's perfectly fine. But for the notation purposes and extracting the formulations, we assume there is Rj for each stage. And again, the main difference between this one and previous system is that in previous system we just had one arrival rate of lambda for the whole system, And those entities would go from stage 1 to stage 2 to stage 3 all the way to stage k. But here in this system, that's not the case. There is a rate of arrival from outside to potentially any of the stages, not necessarily the stage 1. However, also note that when I say lambda j, these are the rate of arrivals to stage j from anywhere. So when I say arrival to stage j, either from outside or inside. Because at the end of the day, if we want to model any one of these systems, because we will learn that we are going to model each one of these stages separately. If I want to model any one of these stages, there are some entities that are waiting to get processed in that stage. These entities are either coming from outside, or these are the entities that got processed somewhere else in this system and now are here in this stage to get processed as well, right? All of them are waiting to get processed in that stage. I don't care if they are coming from outside or some other stages, they are waiting to get processed in that stage. That's all that matters to me. So this lambda j that I put here basically looks at the rate of arrival of entities to any specific stage to get processed. Either they're coming from outside or they are coming from another stage in the system. So if I want to calculate then lambda j for any one of these stages in the system so that I can analyze them independently and separately, then I can say that lambda j equals to definitely rj for, so the rate of arrival to any stage in this system. For sure, those entities that are coming from outside to that stage, they are there. That's one for sure. Also, the entities that are coming from some other parts of the system. So let's assume lambda I represents the rate of arrival to any other stage I, right? We know that when entities get processed, let's say on a stage I, some of them go to other stages with these probabilities, right? So if we assume that this is the rate of arrival to stage I, then Pij of them go to stage J. After they're done at the stage I, Pij of them go to stage J. Stage J is the one for which I'm writing this whole formulation, right? So for stage J, the entities that come to the system are either the ones that are coming from outside, also of the ones inside the system, the ones that are processed in a stage I, any other stage I, some of them end up going to stage J for the operation. And those some are identified with probability of Pij. They are the ones that go from any stage I, any other stage I in the system to stage J. So the sigma is from any stage I from 1 to k. Okay. So that gives me the total rate of arrival to any state j, no matter if they are coming from outside rj or they have been processed somewhere else in the system. And now with probability of Pij, they are going to end up at state j to go through the next operation. Those also form the entities that are waiting to get processed on stage j. So that helps us to calculate the lambda j for any one of these stages. That's the one that we need in our formulations to find L, LQ, or anything. And then we also want for any stage j, we want obviously the rho j to be less than 1 as well. So in a general scenario, if I consider rho j as lambda j over s j mu j less than 1, that means lambda j should be less than sj mu j. There is nothing tricky about this part. This is just a regular condition of rho less than 1 in any one of these stages because we want to treat any one of these stages as a separate queuing system. So here in this scenario, also we are going to treat each one of these stages as a separate queuing system. And this queuing system will be M, Sj, Gd, infinity, infinity, with arrival rate lambda j that we just calculated, and service rate mu j. So this is very important for you guys to, so basically that's the conclusion of everything. So if arrival rates have exponential distributions, service rates have exponential distributions, and again, the waiting times for each stage has infinite capacity. We can treat each one of these stages as a separate queuing system with rate lambda j, where we learn how to calculate lambda j, and with the service rate mu j. So to find L, which is average number of people in the system, we are going to add up L in each stage. Okay, so that's nothing new. So to find L, the number of people in the whole system, we find L in each stage and then add them up. And then to find W, which is the waiting time in the system, we are going to use the formula W equals to L over lambda. But here, lambda is R1 plus R2 all the way to Rk. The lambda that we are going, so I'm going to consider it as lambda star. The lambda star that we are going to put in the formula for W, in the Little's formula to find W, is basically calculating by adding the arrival rate or the rate of arrival from outside to all this, to any one of the stages in the queuing system. Yeah, so this basically represents average number of entities or customers that are coming from outside to this system. And that's the one that we need to put in the formula, in the Little's formula to find W.